Hi everybody, welcome to week 9, lesson 1 for year 6 maths. This week it's all about chance and probability, and today we're looking at expected frequencies versus observed frequencies. So today we are learning to predict and record the outcomes of chance experiments. And the main thing is to tell the difference between expected frequency of outcomes and the observed frequency of outcomes. So we're going to be comparing those two and then explained why the expected frequency and the observed frequency may differ. They may not match up. So this week we're looking at this idea of chance, also known as probability. They're really interchangeable, those terms, so you'll hear me use both of them throughout the week. And it's all to do with this area of maths where we're looking at uncertainty, where we don't have any certainty that an outcome is going to happen. So for example, with a lotto draw, numbers are drawn completely at random, so we don't have any certainty about which numbers are going to be drawn. Same with rolling a dice, assume it's not rigged. The outcome of that dice roll, whether you're going to roll 2 6s or a 6 and a 3, it's completely random. So there's no certainty that you're going to get a particular outcome. Same with drawing a card from a shuffled deck. But it also applies to other areas that aren't just to do with gambling and games of chance. This idea of probability and chance is particularly important in science, where we're trying to figure out, what's the likelihood, what's the chance of something happening. So for example, in genetics, what's the chance of a genetic mutation? And we can sort of determine, assign a probability or assign a chance to that, but it's uncertain whether it's going to happen or not. Same with the field of insurance. Insurers need to know how many accidents are going to happen in a year. Clearly, they can't predict, or they can predict that, but they can't foresee the future. So they make predictions based on data that they have to try to come up with, what's the likelihood that people in a certain area will have a car accident, what kind of cars are going to have accidents, what age group, and then they do their calculations to figure out their insurance premiums based on that. Same with weather forecasting. Now, we often take weather forecasters, they'll say it's going to rain, it's 90% chance of rain today. That doesn't mean that 10% of chance of no rain is not going to happen. It's just assigning a probability there, but there is a chance that it won't rain as well. And same with games in sport as well. So we can assign a probability to whether a team is going to win or draw or lose. But at the end of the day, the result is uncertain. We don't have any control necessarily over the result. So probability, just to repeat, is the chance of something happening or being the case. So for example, the chance of a die landing on a 6, the probability that people have 2 TVs at home where we don't actually know, let's say we're talking about the population of Sydney, how many TVs do they have at home? We don't know that, but based on a sample, we could probably figure out, well, this is a chance that most people have, or this proportion of people have 2 TVs at home. And the outcome, that's really just the result of an experiment or a trial. So for example, the outcome of rolling a die, well, there are 6 outcomes there. You could either get a 1, a 2, a 3, a 4, a 5, or a 6. So now we're going to look at this idea of expected frequency and observed frequency. So I'm setting up a chance experiment, and I've gone to this website random.org where I have a playing card shuffler, and I've set up a deck of 52 playing cards with no joker. So a quarter of the cards are spades, a quarter are diamonds, a quarter are clubs, and a quarter are hearts. So they're my suits. And what I'm going to do for this particular experiment is I'm going to shuffle the deck, draw out a card, and see whether it's either one of these suits. Then I'm going to record it down and see, how many spades did I take out, how many diamonds, how many clubs, and how many hearts. Now, the first thing I'm going to do is I'm going to set up my expected frequencies. So that's how many of these different suits do I expect or do I predict that I will draw out of the deck. So remembering each time with this, each time with this experiment, I'm going to take the card out, record what it is, put it back in, and then reshuffle it. So that way I'm always putting the card back in. It's not like I'm changing the probability there. So my expected frequency, given that there's an even chance of drawing each of these suits, and I'm doing 40 trials, I've said, well, there's going to be expected frequency of 10 for each of them. That way I'm kind of like spreading it out nice and evenly. A quarter of them will be hearts, a quarter of them will be clubs, a quarter diamonds, and a quarter spades. Then I'm going to actually do the experiment, and that will give me my observed frequency. So the observed frequency is what actually happened. And I can see that it didn't necessarily match up with the expected frequency. So even though I expected to take out 10 spades, my observed frequency was 6 spades. Whereas diamonds, I took out the largest proportion of cards I took out were diamonds, so there's 15 there compared to 10. So your observed frequency, it might match up with your expected frequency, but it might not as well. So this expected frequency is just the prediction based on the probability of taking out or getting a particular outcome. The observed frequency is what actually happened, what the outcome actually was. And I've calculated them all here, and I've put a total down the bottom. Another chance experiment we can run is using a spinning wheel. So here I've got a wheel, it's divided into 5 equal sections, and it's got a color for each of those sections. Now I've got 2 blue sections, 1 green, 1 yellow, and 1 red. So I'm going to do my expected frequency again. That's how many times I think it's going to land on any of these colors in 20 spins. So I can see with my wheel, it's split into fifths. So I know a fifth of 20, or 20 divided by 5, is 4. So I've got 1/5 is yellow, so that's going to be, the expected frequency will be 4. I think it's going to land on yellow 4 times. Same with green and red, but with blue, I've got 2 of those sections colored in blue, so it's going to be double that, so it's going to be 8. Now you can see the expected frequency adds up to 20 because that's the total number of spins. So I actually did this. I went to this website, Wheel of Names, and you can spin the wheel. You can create your own wheels, and this is the observed frequency. So this is actually what happened. So I had 11 blue, 2 red, 3 green, and 4 yellow, and that adds up to 20 as well. So there's more blue and less red than what I was expecting, and 1 less green as well. Now, if I did this again, this is a completely random wheel. It's programmed to be random, so I'd probably get a different observed frequency. If I did this experiment again, these numbers would probably be different. Now, you can see they do differ to the expected frequency again. This is just the predicted probability. This is what I think the probability will be, the likelihood or the number of times it will land on that particular color, based on the fact that this is split into 5 equal sections. But this is the actual frequency. This is the actual times it landed on blue, the exact time it landed on red, yellow, and green. So probability and chance, that's what we're looking at this week, is concerned with how likely an event or an outcome is when it's uncertain, whether it will happen or how often it will happen. Expected frequency is how many times we expect an outcome will occur. So it's kind of like, basically thinking, how many times will I pull out a diamonds card, or how many times will I pull out a clubs card, or how many times will the spinner land on blue or red. Our observed frequency, on the other hand, is how many times that outcome actually occurs. And we saw that we recorded that in a table so we could compare the expected frequency and the observed frequency. And we saw that the observed frequency doesn't always match the expected frequency. And this is because of chance. Chance is random, even though we can assign some probability to it and there is a greater likelihood of something happening. That's not to say that it will always go that way. Chance is completely random. That way it could keep on landing on red, even though red is only 1/5 of the spinner, it could keep on doing that. It's not super likely, but it is possible. So that's the element of chance. All right, guys, thanks for listening to today's lesson. I'll see you tomorrow for lesson number 2. Hi guys, welcome back. This is week 9, lesson 2 for year 6 maths for Tuesday. Today we are representing probabilities. Okay, so today we are learning to represent probabilities in a chance experiment using fractions, decimals, and percentages. So to do this successfully, you need to be able to identify the number of favorable outcomes in a chance experiment. Now, this is a new term that I've just used. Favorable outcomes is the outcome we're looking for. So if you think back to my card experiment where I was looking at the different suits that were being drawn out, say I wanted to find the probability of taking out a diamonds card, that's the favorable outcome there. That's the one I'm looking for. And we saw that with that experiment, there was an equal likelihood of drawing out any of the 4 suits. Then you want to identify the total number of outcomes. So in that experiment, there were 4 potential outcomes: diamonds, hearts, spades, and clubs. And there was 1 favorable outcome for that diamonds experiment, for the diamonds card, I should say. Then you'll need to represent this as a fraction, and then we're converting between fractions, decimals, and percentages. Okay, let's get to it. Okay, so we're going to start by looking at this classic probability or chance experiment of drawing a particular color marble out of a jar. Now, before we do this, just a few things. So this is a theoretical experiment. Now we can see inside the jar. If you were doing this experiment to make sure that it's an experiment in chance, you'd either need to be blindfolded or you have to make sure that the jar is obscured so you couldn't see what color marble you're drawing out of the jar. Secondly, this is just a diagram or an illustration of the colors and number of marbles inside the jar. It's not telling you that the pink one is on the top and the green one's also on the top, whereas these orange ones are down the bottom. Just imagine this is completely scrambled. You have no idea where the marbles are in the jar. The pink one might have started on the bottom. This is just an illustration. Sometimes people will say to me, oh, well, obviously the pink one has a greater likelihood of being picked because it's on top. That's not what this diagram is showing you. The diagram is just showing you these are the colors of marbles in the jar, and that's how many marbles are in the jar. All right, now we've covered that. Let's look at the probability of drawing these marbles out. So here are our marbles, here are our colors, and these are our favorable outcomes. So for example, if I was to draw a green marble, well, there's 5 green marbles I can pick. So there are 5 outcomes for green. That's 5 favorable outcomes for the green marble if I wanted to pick a green marble. 2 for purple because there are 2 purple marbles, 2 for orange because it's 2 orange, and 1 for pink. And you'll see that the total number of outcomes is 10 because there are 10 marbles in the jar. Now, to think about this as a fraction, well, we've got 5 green marbles out of 10 marbles altogether. So we can say as a fraction, it's 5/10, or we can also simplify that. 5 divided by 5 is 1, 10 divided by 5 is 2, and make it an equivalent fraction, which is half. We can see that half of the marbles are green. For purple, I've got 2 purple marbles out of 10, so it's 2/10. Again, with orange, 2/10. And for pink, I've got 1/10 because I've only got 1 pink marble out of 10 marbles. So that's representing it as a fraction. And you'll see that the total adds up to 10/10 or 1. That's the sum of the probabilities there. If I wanted to change this into a decimal, well, I'm already dealing with tenths here. So I've got my decimal point here, and I can see I've got 5 here. This is my tenths space, so I've got 0.5 or 5/10. Same here with my 0.2. The 2 is in the tenths place, so it's 2/10. All the way down, if I was to add all these up, they would equal 1. And then as a percentage, well, all I need to do to make a percentage out of a decimal is to multiply it by 100. So I'd move the decimal place 1, 2, it's down here. I need to put a 0 here. And now I have 50%, 20%, 20%, 10%. And you can see that the percentages all add up to 100%. Now, if I wasn't too sort of confident doing these conversions, I can look at a number line like this, and I can see the relationship between the percentage, the fraction, and the decimal. So here 1/10 is the same as 10%, which is the same as 0.1, and so on. So they're all representing a proportion of a whole. Let's look at a different example. Now this time I've got more marbles. So I've got 20 marbles in here now. So again, I'm going to look at the number of favorable outcomes for each of these marbles. So blue, there are 7 blue marbles. So I've got 7 blue marble outcomes, 1 for each of them. 4 green, 4 yellow, 3 orange, and 2 purple, with a total number of outcomes 20. So each of the marbles represents an outcome. As a fraction, I represent it as the favorable outcome divided by the total number of outcomes. And I can represent that as a fraction like this, because we know that a fraction is a self-contained division problem. This 7 over 20 also means 7 divided by 20. Same with green. There are 4 favorable outcomes out of 20 outcomes altogether. So it's 4 over 20, or I can simplify that and make that 1/5. Same with yellow. With orange, it's 3 over 20. Now I can't actually simplify that any further, so that's fine representing it as that kind of fraction. Even if you don't simplify it, if you still represent it as 4 20ths, or 4 over 20, that's completely fine. It's still a valid fraction. It's just not simplified. For purple, it's 2 20ths or 1/10 because I can simplify it there. Now this is not quite correct. The total is 20 over 20, but you can simplify that as well to 10 over 10 or 1. As a decimal, so this is a little bit trickier. Some of these are a bit obvious. If I had like half, I know that the decimal for half is 0.5. You can kind of recollect those ones. Here, 1/10, 0.1. For this particular decimal here, to get that decimal, I just need to follow this. 7 divided by 20 will give me 0.35. Same with 1 divided by 5 will give me 0.2. 3 divided by 20 gives me 0.15. So you could use a calculator for that. That's totally fine. You could do the bus stop method if you like. It doesn't really matter. The main thing is that you recognize that dividing the numerator by the denominator will give you the decimal. And you can see here the sum of these probabilities as decimals is 1 again. So always make sure that if you're doing a table like this, all your probabilities need to add up to 1 or 100%. And then just to change these into percentages, I just multiply them by 100. So here, move the decimal place 2 places to the right, because I'm multiplying by 100, so it's getting bigger, and it becomes 35. And the same with these ones here. So we've looked at describing the probability of a particular event or different events using fractions, decimals, and percentages. Now let's look at organizing a game so that it has particular outcomes based on different probabilities. So let's say we've got this game where a robotic arm randomly chooses a square to drop a ball on, and we want to make sure that it has certain probabilities for different outcomes. So here I want to make sure that it has a 10% chance or a 10% probability of landing on pink. Well, here I've got 10 squares, and I know that 10 times 10 is 100, so 100% would be all of my outcomes. But I also know that 10% is the same as 1/10, so I want to color in 1 square pink. For blue, the probability is expressed using a fraction now, so it's 4/10. So 4/10 of this particular array would be 4 blue squares. For orange, I want the probability to be 0.2. So I know that that's the same as 20%, because just to make it a 20%, I can multiply it by 100. So it's going to be 2 squares, or it's also 2/10 as well, because it's in the tenths place. 2/10 of this, nice and easy. And then for green, it's 30%, so it's going to be 3/10. And if I was to add all these up, I'd probably convert them into one or the other, but they would all equal 1 or 100%. And there you go. So now It has a 40% chance of landing on blue, or a 4 out of 10 chance of landing on blue. It has a 20% chance landing on orange, a 3 out of 10 chance landing on green. So here I'm just converting between those different ways of representing probability. The same principle applies to a spinning wheel. So I've got 8 different outcomes here because there are 8 different sections. And I want to make sure that it lands on yellow, or has a 25% chance of landing on yellow. So what I've done is I've colored in 2 sections yellow because that represents a quarter of the outcomes. I know that 2 is 1/4 of 8. I've got 8 total outcomes. Same with blue. So now I've got 25% for blue, 25% for yellow. Now for red, it's a little bit trickier. What I need to do is I need to say, well, 1, because I've got 1 outcome here, divided by 8, and that gives me 0.125. And then I can multiply that by 100, which gives me 12.5%. And then all I really need to do now, I've got 3 left over. I can either multiply this by 3, because I know that one of them equals 12.5. Multiply that by 3 is 37.5. Otherwise, I could do the same thing again. I could do 3 divided by 8 multiplied by 100. And that would give me the percentage. So the main ideas from today's lesson, this is particularly important, is you can represent the probability of an outcome by dividing the number of favorable outcomes by the total number of outcomes, because we remember this fraction line also means dividing line. So let's say on our spinning wheel, we wanted to get yellow. We had 2 yellow sections, and we had 8 sections altogether, so 8 different outcomes, 2 yellow outcomes, so 2/8, or I can also represent that as a quarter. Now this can be converted to a percentage or a decimal. We know that a quarter is the same as 25%, or also if I wasn't too sure about that, I'd just go 1 divided by 4 equals 0.25. Now, the larger the fraction, the percentage or decimal, the greater the likelihood that the outcome will occur. So a percentage of 75% has a greater likelihood of occurring than an outcome with a 25% chance. We can increase the likelihood of a favorable outcome by increasing the number of favorable outcomes. So for example, on that spinning wheel, if I wanted to make yellow increase the likelihood of yellow, then I just increase the number of yellow sections. So I could increase it by another 4 sections, then I have 6 sections over 8, so 6 divided by 8, and then I multiply that by 100, and that would give me my percentage probability. And lastly, all probabilities must add up to 1, so or 100%. Now, just because, I think I've said this before, just because it has a high probability of occurring does not mean that after a certain number of goes, you will get that probability. You could keep on getting the least probable outcome. That's just the way chance goes. But it does mean there is a higher likelihood of it occurring, particularly after a lot of trials. But we'll look at that tomorrow. All right, guys, I hope you enjoyed today's lesson. I'll see you tomorrow where we're looking at the difference between small trials and large trials. Welcome back, everybody. This is lesson 3 for week 9 for year 6 maths for Wednesday. And today we're looking at probability, where we have small and large trials and experiments. So increasing the number of trials that we do in a particular chance experiment. So today we're learning to describe probabilities in experiments involving small and large numbers of trials. So trials in this context means how many times do we do a particular experiment? For example, how many times do I spin the wheel? How many times do I roll the dice? How many times do I take a card out of a pack of cards? Each of those is a trial. We're going to be distinguishing between expected probability and observed probability, which I'll go through in a minute. conducting experiments involving small and large numbers of trials, and explaining the effect that a larger number of trials has on the observed probability. So what do I mean by expected probability and observed probability? Well, expected probability is what we've been looking at so far. It's the chance of events happening under ideal circumstances, so under perfect circumstances. So this is saying you could remove chance from the equation. There was no element of randomness. So we want, let's look at our spinning wheel here. We've got 5 sections and I want to get blue. So 2 of those sections are blue. So that's 2 of my 2 favorable outcomes. And there are a total number of 5 outcomes. So under ideal circumstances, under perfect circumstances where there was no chance, for every 5 spins of the wheel, 2 of the times they would land on blue. Now we know that's not how chance or probability works because of that element of randomness, that element of chance, but this is under ideal circumstances. Observed probability, on the other hand, is what actually happens in reality. So the number of observed outcomes, so how many times does it land on blue? So let's say we span it, or spun it, I should say, let's say we did it 5 times and it landed on blue none of those times. Then we put a 0 here and we spun it, sorry, why I keep on saying span it, spun it 5 times, and that's our total number of trials. So the observed probability is 0/5 or 0 or 0%. Yep. So there is a difference between expected probability of what would happen in a perfect world without chance, without randomness, and observed probability, what actually happens when we do the trials. So let's look at our spinning wheel in a little bit more detail and look at the difference between the expected probability and the observed probability. So here I've got all my different colors, blue, red, green, and yellow. These are all the possible outcomes of spinning this wheel. And these are the number of favorable outcomes for each of these colors. So the number of blue sections is 2. So there are 2 blue outcomes. There's only 1 red section, so that's 1 red outcome, 1 green, and 1 yellow. So a total number of outcomes from spinning this wheel, because there are 5 sections, there are 5 different outcomes. So my total number of outcomes is 5. Now to find the expected probability, I know that I need to divide my favorable outcomes by the total number of outcomes. And I can represent that as a fraction. So 2 divided by 5 or 2/5, 2/5. I can also show that as a percentage by dividing 2 by 5 and multiplying it by 100, which gives me 40%. And for these ones down here, red, green, and yellow, they all have the same chance or the same probability because the expected probability is 1/5 or 20%. And you can see down the bottom here, I've added up all the probabilities to be 5/5 or 5/5, which is 1 whole, or 100%. So basically what this is saying is if you spin this wheel, you will get any one of these colors. There's a 100% chance that you'll get a color spinning the wheel. Now this is the observed frequency. So this is from 20 trials, which I did last time. It landed on blue 11 times, red 2, green 3, and yellow 4. So the observed probability is the observed frequency divided by the total number of trials. So here I've got 11 divided by 20 or 11/20ths, and I can make that into a percentage, which is 55%. So here my observed probability was actually different to my expected probability. The observed probability for blue was actually greater than what we expected. Same for, well, opposite goes for red, because for red, the expected probability ended up being, had 2 times that it ended up being on the red. So that's 2 red outcomes over a total number of trials is 20, which is 10%, and you can see the remainder of the results here, and they all add up to 100% or 1. And so you can see here for red, the observed probability was 10%, but the expected probability was actually higher, it was 20%. So what actually happens if I increase or decrease the number of trials that I run? So here, I didn't just spin it 5 times, I spun it 20 times. I could increase the number of trials if I want. Would it change the observed probability? Well, let's have a look. This is a different experiment now, just to change things up a little bit. This is rolling a 6-sided dice. So assuming that you're rolling the dice so that it's not rigged and it's under perfect circumstances, this is the expected probability. There are 6 outcomes, a 1, a 2, 3, 4, and 5, and 6. So what I need to do is I need to go 1 divided by 6, or 1/6, and that will give me this percentage. It's not a particularly neat percentage. Dividing 100 by 6 or by 3 always gives you a recurring number. So in this case, I've actually rounded it up to 1 decimal place. Now here, I've done this on a random dice generator, which I've given you the link for a website called GeoGebra. And you can select the number of times you want the dice to roll. So you're not constantly having to click. You can go, I want it to roll 20 times or 10,000 times, and it'll just do all those calculations quickly and give it to you straight away. So this is the actual outcomes. This is the observed frequencies. It landed on 1 4 times, landed on 2 0 times, and so on. So these are my observed probabilities. 20% for 1, so it's actually greater than the expected probability. 0% for 2, so it's well out of the quite far away from the expected probability there. It actually really doesn't match up very neatly for any of them, to be honest. This one is lower, and these two are considerably higher. Now, what I did for this was I increased the number of trials. So instead of doing just 20 trials, I ended up doing 10,000 trials. And you can see here, the expected probability still stays the same because there are only 6 outcomes. So the expected probability stays the same regardless of how many trials I do. But the observed probability has changed. So you can see here, if you look at the graph, the outcomes, the observed outcomes, are much closer together than they are when I just did 20 trials. And we can see that with the observed probability, that's much closer to the expected probability. So the more trials I've done, the closer the expected probability and the observed probability are to one another. So the observed probability starts to match the expected probability the more trials I do. So the main ideas from today's lesson, it's really around these two concepts of expected probability and observed probability. Expected probability, that's the calculated probability in ideal circumstances. So let's think about our spinning wheel, and we want it to land on blue. And we remember that there were 5 sections altogether. So that's our total number of outcomes because there are 5 different outcomes, and 2 of those were blue. So that's our expected probability, 2/5, or 2 divided by 5, which is 40%. If we change it into a percentage. The observed probability, on the other hand, is the number of favorable outcomes achieved divided by the number of trials. So it's a different way of calculating the observed probability. So let's say we did that experiment 30 times. That's my number of trials. And it landed on blue 17 times. That's my favorable outcome. So the observed probability is 17 over 30. And lastly, the greater the number of trials that we do, the greater the likelihood that the observed probability will begin to match the expected probability. So the more trials you do, if you keep on doing it, eventually it will start to match the expected probability. We often call it theoretical probability. That's the ideal probability, just based on calculating the number of favorable outcomes divided by the total number of outcomes. All right, guys, I'll see you tomorrow for your last lesson on chance. I hope you enjoyed today's activities. Bye-bye. All right, now we come to our last lesson for the week, lesson 4 for year 6 maths. Today we're predicting probability using samples. So today we're learning to use a sample to make a prediction about a larger population. Firstly, you need to be able to distinguish between a sample and a population, which we'll look at in a moment. Calculate the expected probability of a result based on a sample, and understand why samples are used and how they relate to chance. So population and sample. So population is the entire group of something that you are trying to find information about. So for example, the population of Australia is about 27 million people, but I might get a sample of people to find out something about the Australian population. It's quite difficult for a population that size to kind of survey every single person. So what I might do is I might form a sample group, get together some people, ask them some questions, and use that information from the sample to make some conclusions about the broader population. Now, in that case, I'd want to make sure that the sample was representative, that it had people from all different backgrounds, different ages, different genders, so it wasn't a skewed sample. It wasn't just, I'm just surveying men in their 40s, or surveying women in their 20s, or surveying people from Sydney, for example. I want to make sure it's representative. Now, there's quite a science around forming a representative sample. You don't need to worry about that today, thankfully. We're going to do some crude sampling and just using those samples to predict the probability of an event or something about a larger population. So we're going to look at a jar of gummy bears, and there are 100 in the jar, and they're either yellow, red, or green. And what we're going to do is we're going to take a sample out of the jar and try to predict what proportion of the jar is yellow, red, or green. Now, this is only 100 gummy bears, so you could technically empty the jar and do a breakdown that way, but we're just doing a nice, simple sampling exercise. So let's start off with our first sample. So I've reached in, grabbed 5 out without looking. So I've got 1 yellow, 3 red, and 1 green. And I can break this down. Out of this group, out of this sample, 1/5 is yellow, 3/5 are red, and 1/5 is green. So I could use this sample and say, well, this represents what the actual breakdown of gummy bears in the jar is. 60% of the bears in the jar are red, 20% are green, and 20% are yellow. That's one sample that I've done. Now what I'm going to do is I'll put these ones back in the jar, shake it up a bit, and then take another sample. This time around, I've got 3 green, 1 red, and 1 yellow. So now the sample breakdown is different. I've got 20% yellow, which is the same, but now I've got 20% red and 60% green. So now I might conclude, well, actually that first sample, maybe that was just a lucky one for the red bears, but actually there might be fewer red bears in there and more green ones. So actually it's 60% green rather than 60% red. So you can see that the 2 samples have changed my predictions. What I can do now is I can go, well, actually, each of these samples, there's 5 bears, there's 100 bears in the jar, so each of them represent 1/20th of the contents of the jar. I could combine these 2, which actually makes 10 bears in total, which now is 1/10, so it's a larger sample. And from this, I can also make a new prediction. So actually, I've got 2 yellow bears here, so now it's 2/10, or it's still 1/5, so still 20%, still the same. But now I've got 4 red and 4 green. So I've got 40% are red and 40% are green. So again, this has changed my prediction about what's in the jar. Okay, so beyond trying to predict how many lollies are a particular color in a jar, which is a classic probability exercise, there's also a crossover between probability and chance and data. So a few weeks back, we looked at data, looked at surveying people about their preferences, putting that into tables, either into two-way tables or into graphs. And there's a big crossover between data and chance, because usually when we do a survey, we can't actually conduct a survey for everybody within a population. So for example, let's say you own a shoe shop and you want to know what color Converse do customers prefer, because you want to order some in, you want to make sure that you're getting the sales, so you want to make sure you're catering for your customers. So you end up doing a survey of 1,000 respondents, and let's say you're targeting 18 to 35-year-olds, that's your demographic, and these are the results of the survey. So 1,000 people have been surveyed, and we've got white, black, red, yellow, and blue, so they're the colors, and these are the survey results. So based off this, you can see that 71 people liked white out of 1,000. So I can represent that as a fraction, 71 over 1,000, but I can also represent it as a probability. Now, this is where there's a crossover between observed probability and expected probability. So from this survey group, I might be able to conclude that, well, actually, from 1,000 people, that's a pretty large survey, particularly for a store. So I'm going to order more of the red ones, because there's a probability of about 40% that people will tend to buy the red ones. Then there's a greater probability that people will buy blue ones or prefer to buy blue ones than white ones, because white ones seem to be the least popular. There's only a 7.1% probability that people will buy white. So that's where there's a crossover between using survey data and chance. We don't know what people will buy. We can't kind of go into their heads and predict in the future or on any given day, but it's trying to give us some level of certainty about what people will buy. We know at the end of the day, it's completely uncertain, it's completely random who walks into the store, what they buy, but this survey gives us some idea, some probability about what color Converse people will buy. So just to wrap up, here are the main ideas from today's lesson. So samples can be used to make a prediction about a larger population. That's using probability. So for example, with our shoe store example, the probability that people will buy red Converse. We don't know for certain whether they will buy red Converse, but there's a greater probability or a greater likelihood that people will buy red Converse than, say, white ones, based on the results of that survey. We also want to look at the breakdown of the sample, and we can apply that to a population. So for example, say I had 10 gummy bears from that jar, and 50% of them were green, so 5 of them were green. Then I can reasonably predict that 50% of the jar will be green gummy bears, and I can scale that up. So let's say there are 200 gummy bears in the jar. Well, now I can say that 50% of the jar is green, therefore 100 gummy bears in the jar will be green. That's my reasonable prediction. Now, I could be completely wrong, but it's giving me some idea of something that's unknown, that's uncertain. Okay, guys, I hope you enjoyed this week on chance. If you have any questions, feel free to send me a private message on Google Classroom. I'm more than happy to help, and I'll see you next time. All right, bye-bye.